everyone. No, I shouldn't be here. So I'm going to present a few theoretical guidelines for workflow design. So it's based on around 2 years of experience in trying to write workflows. And as you know, I mean, trying to communicate experience through slides is not always an easy task. But I'll do my best and to give you at least a few take-home messages that you can try then to apply in your everyday life when you write workflows. So the plan is the following. So first, I will explain what is a workflow and when do we need it and when do we not need it, actually. Then a few basic rules just to give you an insight. I will talk specifically about the fact of sub-workflowing when you want to write sub-workflows and give you examples for this and the rest. And finally, I will talk a lot about provenance and its fragility. So to begin with, what's a workflow? So first, let's say what they are not. So a workflow is not just something useful for high throughput. So you might think, okay, I don't care about high throughput, so I don't care about workflows. This is typically a not correct statement because you might be interested in a very complex task that has lots of automatic steps and this complex task, even if you do for a couple of different materials or structures, is still very interesting to encode it in a workflow. And a workflow is also not something that is just replacing your great bash scripts that you were using before you realized you could do lots of stuff with IDA. It's not about this. It's not just scripting things in another way with another language. It's something a bit more evolved. So what they are actually, workflows, is really a way to automatically launch some time-consuming tasks that are logically depending on each other. So all this sounds obvious, but it's good to repeat it. So, and the key point is that you shouldn't have to wait for each of them. There should be something waiting for you so that you don't have to wait and press enter to make the next task. It's really something that will automatically launch these tasks all together. And the workflows are really relying on some clear and really robust scientific knowledge. So something you can encode to make it reproducible. So if you don't have it, it's even useless to try to think about a workflow. In the end, the workflows, they are producing provenance compliant results at the caveat that they should be properly designed. And actually, I will show you some traps that you can easily fall in when you won't respect provenance. So this is something I will talk later. So in short, a workflow is a way to organize and to rationalize all the boring part of your work so that you can focus on something that is much fancier. So really it's about organizing stuff. So when should we use a workflow? So again, when you don't need a workflow, if you're just making a loop, for instance, I have this bunch of structures and I just want to compute the total energy. For this, you don't need a workflow. You just write this loop in Python and you launch it and it's fine. But as soon as you want to do some post-processing on top of it, then you need a workflow. Anything that requires you waiting for the result and do something on top of it. So for instance, after I computed the energy of this bunch of structure, I would like to get the lowest energy one and compute the band of this one. Then here, you need something called a workflow. It will ease up your life, let's say. So if anything is not clear, let me know, but I think a few basic rules for a good workflow design. So all these might sound trivial, but it's always good to repeat because it's very easy to forget them, especially when you're in the flow of coding and then you don't want to think too much. Actually, it's always good to take a few minutes, maybe even a few hours to think more about all these things. So first initial thing that the problem you want to solve with a workflow should be really well defined. And you know how to solve it, most importantly. You know how to solve it in general. So it means you need really to review carefully all this process before even trying to write a workflow. So you should have an algorithmic method that is able to handle all the possible cases, and this without any human intervention. Then the most important things about workflow is that inputs and outputs should be extremely clear. So, for instance, the input parameters, you need really to work on the labels, on the keys. It should be extremely clear, extremely precise. And it's like when you look at an old Fortran 77 code and you have all these A1, A2, A3 variables. Think about what you will see in 6 months when you go back to your code and have a label that is something like a SPG. What is SPG? Is this space group? Is it J vectors of a species? Whatever, something stupid. So you need really to think at the label and what somebody else will think when he would look at it. So the best is actually to show them to somebody else, and this somebody will tell you if it's clear or not. The output is the same. You need really clear, precise labels, and you should also avoid just a scalar, so you output just the energy like this. You should always put stuff in at least a dictionary, and if it's an array, in an array data, so that it's encapsulated in an AIDA object. Also, the point of a workflow is to hide all the intermediate steps that you don't need to know about. So you should not keep systematically all intermediate calculation as a result, but you can keep those that are interesting in themselves. For instance, if you have a workflow that computes the total energy and then the bands, you keep the bands, but maybe you also keep the total energy calculation because in itself it has some important information. So those you might think they all sound trivial, but and there are probably some that I forgot. At least if you have this, it becomes a quite clear situation. So now it's quite natural when you have a workflow to try to create subtasks. So this is done by sub-workflows typically. So you have a very complex task to compute, like I want a phase diagram of something, and you know that you have to compute the total energy, the phonons, etc. So there are a lot of subtasks that are clearly defined. Now, this is the typical top-down approach when you think at a bigger problem and you itemize each of the tasks. So sometimes it's the contrary. And actually, it's more rare, but typically you can also have already some simple workflows doing some tasks, and you build on top of it something more complex. And that's the bottom-up approach. And actually, typically, the sub-workflows that you did with the bottom-up approach, they are clearer because they were defined to solve a given task that was given from the start, while those that you did from the top-down approach, they are more oriented toward the more complex task you are trying to do. And it means that actually those with the bottom-up are typically clearer. You have thought better about what you want to solve in this one. So they have more an interest in itself. And that's better. So actually it means that those that you did also with the top-down approach, because it does happen, you should think about them as single task solvers. So as having an interest in itself. Because then you can, you might use it later for something else, or you might share it with somebody that will just need this specific workflow. And if you have, from the start, thought about what you could do really with this subtask, it will be much easier to share it with somebody. So I'm going to give examples about this, which is the phonon dispersion workflow. So the phonon dispersion workflow, in essence, is a quite simple workflow that is aiming at computing a full phonon dispersion of a material. So you begin with a structure relaxation. So you have a given structure and you just relax it. And then you compute dynamical matrices. And finally, you finish with some Fourier interpolation that is typically done in 2 steps. Interatomic force constant in real space, and then the phonon dispersion. So this sounds very simple, linear, and easy. Now, actually, those 2 steps here, the last ones, are just single calculation. But those 2 here, well, when you begin with the structure calculation, you might say, okay, I just launch a calculation and that's it. But then when you do it practically, you realize that there are lots of cases when it fails for some reason. Just maybe the cluster is limited to 2 hours and your calculation took 2.5. So you need to restart it after. So you will need to begin to handle lots of possible cases just for this step. And if you try to do everything inside this workflow, at some point you will end up with a very complex code that does too many things. Well, actually it's better to make a sub-workflow. So that's when the virtue of sub-workflowing is appearing. So you really do a subtask here that is solving the structure relaxation problem in itself. And then you begin to really do a sub-workflow. And for this also, for the dynamical matrices, you also need to sub-workflow. So all these are sub-workflows that should be thought in themselves in what you want to solve as a problem. So for instance, this one here is called the energy workflow, or actually the PW workflow, because it's more oriented toward quantum espresso now. And this sub-workflow is used in many different workflows. It's actually the one that I'm exchanging the most with other people. And when you think about it, it's really simple. You just have a structure, some input parameters, and you begin an energy calculation that you restart if it fails for some reason, and you also try to make sure the volume of the relaxations of the relaxed cell is well converged. On top of it, if you want, you can compute energy bands, and in the end you have all these output parameters and structures and bands. So this, since it's really solving something in itself, is used in other workflows, for instance the CHRONOS workflow. So the CHRONOS workflow is something to given a structure, try to find the magnetic ground state. Yes? Sorry.
So when you said in the beginning that if you do a single calculation, you don't need a workflow. In the end, you always do need a workflow, because you have to handle problems with the...
Yeah.
In the end, basically everything is a workflow.
Yeah, everything is a workflow, I agree. There might be, I mean, in the beginning I just said, if you really have a calculation that is extremely simple, that you never need to restart, like it's done on your own computer anyway, then maybe you don't need a workflow. The example I could give that is from real life is this stuff here. So here, this is something I do typically on my computer. It takes half a minute, and there I don't need I never experienced I needed a workflow. So it's based also on practical consideration, but I agree. In essence, yes. So the CHRONOS workflow is something to get the magnetic ground state of a structure when you don't know anything, and it's a workflow that begins by generating some different calculation to check all the, not all, but a few possible states. So it first checks a non-magnetic calculation, and then it also tries to put some magnetism inside, and you need to specify some starting magnetization that you do randomly, essentially. And then there are some different possibilities. So if at this step you see that those could lead to a non-zero total magnetization, then the structure is potentially magnetic, and you want to continue with something else where you go in more general antiferromagnetic order states. Otherwise, you just know it's probably really not magnetic, and you can just take the non-spin polarized configuration. So at this level, you need to generate supercells or different structures, configurations that we do using PyMagen. So it gives me the occasion to say something that Giovanni said yesterday, that we are not trying with AIDA to redo everything that is done in other libraries. So actually, it's very good to use stuff like PyMagen, ASC, SPGLib, that are those super well used libraries around. That you can very easily plug in some AIDA code and do stuff around. So here it's used just to generate different possible structures, and from these new calculation. So I don't want to go too much in the details, but I want to insist on a few things. Why doesn't work? Okay. That these things are done with this energy workflow I just told you about, and you see here that it had an interest to design it properly, just to make a good relaxation, and not only really making it too specific to the phonon problem, because I can reuse it here, and that's the power of sub-workflowing. So this workflow gives me a bridge to the provenance thing. So this is the theoretical flow chart of the workflow, but then if you go in practice in what the database will look like after you launch it, you see that everything is well connected. You cannot really see all the boxes, but essentially you have some data, some calculation, some code with this thing here. And there is no gap in between all this stuff. I mean, there is really some links between the initial parameters and structures. The structure is the structure somewhere here. Yeah, here. Actually, it's coming from something else before. And until the final parameters, that is just something where I summarize the magnetic state and the metallic state also. So everything is well connected. And actually, it's very easy at all these steps to lose one connection. And I'll show you a very simple example. That's a typical mistake that is easy to fall in. So you create a supercell. So ASC is very good to create a supercell. You just take the structure, you take the ASC object corresponding to the structure, and you multiply by 2, and you get a supercell. And you build a structured data from it. It's a one line. You're super happy. You think that you use the power of AIDA to its beauty. And you end up with something that is actually not connected. So this supercell is not at all connected with the initial structure. And when you lose just one connection, you lose everything else. So anything you will compute on top of this supercell, you will not know what it comes from. So if this structure was coming from a complex project and the process of building this structure in some way, then you totally lost everything and you're not able to reproduce what you're going to do after. So provenance is something fragile and you have to be careful. So it means that in those steps here, I need to put something that creates the links between all these things. So I need to really encapsulate the structure generation in something that creates all the links for you. And that's easy. AIDA is done for this. So you just need to think about it. That's the point. So in that case, the cure would be just to create a work function. Formerly it was called inline calculation, but it's the same principle. That will encapsulate just this line into a small function that will connect the input, that will be my structure in that case, to the output that will be my supercell. So the provenance should be kept for all kinds of data that are meaningful to calculation. So there are still some exceptions in a way, because if you really connect everything to everything, you end up with something that sometimes is too complex for nothing. So example, when you have some input parameters that don't really have an effect on the final result, for instance, conversions parameters like, stuff that is helping conversions like the beta mixing or whatever, this thing, it's arguable if you really need to include them in the provenance or not. You may not. It's not a religion provenance. You still have some possibility to play with it. But all the important stuff, like the really meaningful parameters, the structures, all these things should really be connected. Otherwise, you just lose the essence of what is AIDA, that is trying to reproduce stuff. So just as an example, again, in this workflow, what you end up is being able to define some magnetic moment that you can then reuse to compute the magnetic ground state of the structure. So it means that those input parameters, they are important and you want to keep track of how you obtain them. While other input parameters, like I said, beta mixing or whatever, it's arguable if you really need to keep provenance on this. For sure, it's something you need to think about. When you design your workflow, you need really to think about the provenance. So I'm done. I hope I was not too boring, but I want to finish with a few take-home messages. So use clear labels for inputs and outputs. That's really important for the portability, the usability of your workflows by somebody else, or even you in 6 months. You should make reusable sub-workflows. So think bottom-up rather than top-down. And think about provenance that is very fragile. Make sure to keep it for important stuff. That's it. Thank you.
Are there any questions? Well, one is not related maybe to workflow, but in general to AIDA, and so we talked with Martin yesterday. So what is your recommendation? So when you open and close notebook while AIDA is doing something, so it may kill all your file transfer. So what do you do? What's the best way to shut down? Because when you go home, so you close the notebook, but it is transferring something.
Just
then it will kill.
Just stop the daemon.
Stop the daemon.
Yeah.
Or don't use the laptop. I mean, in practice, you want something which is running in the background. So I mean, if you are trying and you stop the daemon, it works. But in practice, for real production application, maybe you want to use a workstation, which is always on.
No, it's not true. This is not true. So people will use notebooks, and if the best way is to shut down the daemon before going home, this is what they say.
Yeah.
So it will stop all the transfers.
No, well, it will just stop initiating new stuff. Actually, the ongoing transfer, you should also wait that they finish, because you might indeed lose them.
So if I shut down the daemon while it's transferring something, will it kill it?
No, we just wait.
You will just wait. I mean, if you, then maybe check the calculation states. If you have something like retrieving, wait a few minutes, if you can. Don't shut down. Well,
you can shut down the daemon.
Yeah, you can shut.
The daemon will not really will say I'm waiting until when.
But actually, yeah, there's no simple answer to this, I would say, except just try to shut the daemon. Indeed, as Giovanni said, it's always better to have something that always runs.
Well, you can lose the connection, so it was.
Yeah, but yeah.
Also, everyone's.
Anything else? Yes.
Maybe this is ahead of things, but imagine you are doing this magnetic workflow, and in the course of generating new structures, one of them turns out to be metallic, whereas the previous ones were insulated. Then you need to refine your cake on something.
Yeah.
So you have some insight into that. You should be doing a convergence workflow inside the workflow. Right?
Yeah. Well, yeah, and actually, when you begin to think of this thing, you realize you can at many steps do some conversion tests. So in practice, you don't do it. Or I mean, that's the problem with workflows. You need to rationalize in a way that you think that is maybe not the best way, but that works in general, essentially. So typically, this I don't do. It would be better if I do, but then I have other things to do in the same way elsewhere. It becomes very complex. So my idea is more, you begin with some ad hoc parameters for the K-point sampling. You try to do all these tests, and when you think you're more or less sure you found the ground state, that is, for instance, magnetic and insulator or magnetic and metallic, then you refine everything in the final structure you found. That's the main idea. It means that you're making mistakes sometimes, but the idea would be that most of the time it's working in this kind of workflow, because it's really a workflow for high throughput stuff. So maybe you miss 5% of the case, I don't know, but in most cases it should work. That's the idea behind.
Okay, so you can continue now with the workflow part.